everyone. This video is going to be on logarithmic functions. So towards the end of the exponential functions video, we ended up with an equation that looked like this: a raised to the power t star is 2, and how do we find t star? So this is an exponential equation, and to solve this we need tools, we need the right tools to do it, and that's where logarithmic expressions and logarithmic functions come into play. Now, just a quick primer or a quick review on logarithmic expressions. So 2 raised to the power 6 is 64. Can equivalently be written, an equivalent way of writing that expression is log 64 to the base 2 is 6. So the way I remember it in my head is 2 to the power 6 is 64. Similarly, 3 to the power 4 is 81, which is what we see here. So in more general terms, if b to the power p is a, then log a to the base b is p. So b is base, p is the power of the exponent, a is the argument. And I listed out a few more examples here. Be sure, please play around with that and make sure you understand the logarithmic way of writing an expression such as 5 power 0 is 1. Okay. Now, log a to the base b is defined only when b is greater than 1 and when a is greater than 0. Now, let's look at a few cases where we wouldn't want any other values of b. Now, let's put in b is equal to 1. Suppose I have an expression, say log 5 to the base 1 is p. Then that leads me to 1 to the power p is 5, which is an invalid expression. So you can never have a base 1 in the way of writing logarithmic statements. Now, let's look at b is equal to 0. Why would we not want that? Now, if I write a statement like log 6 to the base 0 is p, 0 is the base raised to any power. It's going to be, and you see how in this particular example this breaks down. So b cannot be 0. Now, let's look at why we wouldn't want b to have any negative values. Now, suppose I have, say, some log of y to the base minus 2 is equal to 1/2. So minus 2 to the power half is y, which is just another way of saying square root of minus 2 is y. And that expression is not defined in the real space. Therefore, b cannot be less than 0. So you now see why b needs to be greater than 1 for the log of this expression log a to the base b to be valid. Now, why do we say that a also has to be greater than 0? Now, b to the power p is a. And we now know that b is strictly greater than 1. And any number which is greater than 1 raised to a particular power, whatever the power may be, positive or negative, is going to be greater than 0. And therefore, a, which is equal to b power p, is also greater than 0. And this is just a brief explanation behind why we say log of a to a particular base is only valid for positive values of a. Now, when we use logarithms, there are two bases which are commonly used. One is base 10, and that's written as, say, log of any number to the base 10, and that's just generally written as log of x. The other common base that we use, and very often in economics, is to the base e, log of x to the base e, or so on. And that is called the natural logarithm, and it's referred to as ln of x, which is written this way. Another way of ln of x is just ln of x to the base e. It's just that because you put natural log here, it's not necessary to put an e at the base there, but these two are equivalent. Now, as I mentioned earlier, why do we need log functions? Because we want to be able to solve exponential equations of this form, a to the power x is b. And these kind of questions feature frequently in examples like these. When will prices triple? When will world population growth double? If I put a certain amount of money in a bank account, when will I get 10 times the amount of money or 15 times the amount of money, and so on. So to be able to solve for how long something will take, that's when you have an exponential equation. And the way in which log helps you transform an exponential equation, that is where it comes in handy. Now, let's do a few definitions about natural logs. Now, natural logs are where the log is to the base e. So, an expression like e power x is 4 is written as log 4 to the base e, or I'm sorry, this has to be I can write it this way, hold on. So log 4 to the base e is x, or ln 4 is x, is another way of writing it. Or, and in the second example, this expression can be translated into something like into this, and this is just log 3.2 to the base e is minus 3x, and this is just ln 3.2 is equal to 3x, and so on. Now, let's do a couple of definitions here. If e to the power u is a, then ln of a to the base e is u, which follows straight away from how we define the logarithm. And now u is called the natural log of a. So if e power u is a, then u is just ln of a to the base e. And now, given that we have an expression for u here, if we plug that back into the first expression, we get e power ln a, it's just a. Okay, and all of this just derives from the way in which logarithms are defined. Now let's do a few examples to understand how this ln function is distributed. Now, what is ln of 1? Ln of 1 is just nothing but ln 1 to the base e. And let me call that x. If ln of 1 to the base e, okay, I think what I'm going to do is I'm just going to quickly solve all of these here so that it looks clearer for you. Sorry about that messy writing. Hopefully, when I rewrite it, it will look cleaner and easier for you. Okay, let's solve this. So ln of 1, if let's say ln of 1 is equal to x, okay? Ln of 1 is nothing but ln 1 to the base e. So an equivalent way of saying this is I want to find x such that e power x is 1. Therefore, x is 0. Therefore, ln 1 is 0. Now, let's find ln e. Let me call this x again. And an equivalent way of writing this expression is that e power x is equal to e. Therefore, x is equal to 1. And ln 1 is equal to, ln e is equal to 1. In a similar fashion, if ln 1 by e is equal to x, I can rewrite that as e power x is equal to 1 by e. Therefore, x is minus 1. Ln 4 is equal to x can be rewritten as e power x equal to 4. Just take out your scientific calculator, and you know that e is 2.7. So e squared is going to be bigger than 4. So your x is going to be a number which is less than 2. So just plug in a few values and you should be able to find it. Okay, ln minus 6 is equal to x. This translates into e power x is minus 6, which cannot be possible because e is positive, and a positive number raised to any power is going to be a positive number. Therefore, this is undefined. Therefore, ln minus 6 is undefined. Ln 0 is x becomes e power x equal to 0, which again, for the same reason mentioned earlier, the positive number raised to any power is positive. It cannot be 0. Therefore, ln 0 is undefined. And we want to find ln x where x is less than or equal to 0. And we just see from the earlier examples here, minus 6 is undefined, it's a negative number, 0 is undefined. Therefore, ln of x is undefined when x is less than or equal to 0. Okay, a few quick rules for natural log functions. If both values, if x and y are positive, the ln of product xy is just the sum of ln x and ln y. If the numbers are positive, ln of the quotient x over y is the difference between ln x and ln y. If x is positive, ln of x raised to the power p is p ln x. A few examples where this is useful. I've put this down here so that you can look at this as a means of reference. Now, just summing it up, ln 1 is 0, ln e is 1, and for any general x, ln e power x is x, because this is just, e raised to the power x is ex. And we also have x equals e power ln x, and that comes from how we derived this initially. If we have this expression, then u is given by ln of a. Therefore, plugging this value of u back into the initial expression, we get e power ln a is a, which is just, instead of a, I put x here, and that's how we end up with this expression. Now, what's the logarithmic function? It's just the function of ln of x. So, g of x is ln of x. So, in this graph, we go ahead and plot out the ln function, and it's defined only for positive values of x. It is undefined at x is 0. And we have values of ln 1, ln 2, this is I think ln e, which is equal to 1, and so on. And that's how we plot the logarithmic function. So in the next and the final video, I'm going to quickly go over inverse functions and show you the relationship between log and inverse functions. So see you in the last video.